Hello and welcome back to Introduction to Robotics. I'm John Steele and this is the lecture on DC motors and actually some of the modeling for DC motors. And in a later part of this lecture I'm going to talk a little bit about programming these motors to turn using Arduino C. So let's get started. Here's a graphic that shows you the layout of a DC motor. In particular, the rotor is there, as you can see, and a set of brushes in contact with a commutator. And as you can recall from your physics, when current flows through a loop of wire, there is a field, an electric field that's generated. And in this configuration shown here, the field in that loop of wire interacts with the magnetic field from the so-called field windings, in this case really permanent magnet for a DC motor. And it's the interaction of those two that creates the torque that causes the rotor to rotate. And note that it's the creation of the commutator which at the appropriate moment switches the direction of current flow in the rotor windings that allows the motor to continue to rotate. Since if that were not there, then once the magnets had aligned with their opposite poles, they just stop rotating. So the trick of DC motors is this set of brushes in the commutator, which keeps changing the field direction in the armature, in this case, that is the rotor, and keeps the motor turning. That is what we refer to as a brushless, or I'm sorry, a brush DC motor. And brush DC motors are the most common, but they suffer from the fact that the brushes have to be in physical contact with a commutator, and because they're mechanical devices and they are getting loaded, they will wear out eventually. So that's their downfall, as it were. They eventually need to be replaced. So brush DC motors are very common, but they do have some issues. So that's, again, a cartoon. I do have a link on the lecture notes that you can upload from, or you can download, I should say, from the Blackboard site that will show you some other examples of DC motors and their action. Okay. A couple of comments about voltage and current. So DC motors are defined or are expressed in terms of their recommended voltage. So you'll find 3-volt motors, 6-volt motors, 12-volt motors, 40-volt motors, etc. And they are designed to operate with those particular voltages. Most motors will run just fine with lower voltages down to a certain point, but they'll be less powerful. And most will operate at higher voltages than their so-called rated voltages at the expense of operating life. The thing that really kills DC motors is heat. The heat causes the insulation between the windings loops to break down, and once you have that breakdown, you have a short, and then you get much larger currents flowing, and then you get more heat, and the motor is dead. So if you want to run a 3-volt motor at 6 volts, feel free to do so, but recognize that if you run it at that voltage for any considerable length of time, you'll be buying a new motor. the exact duty cycle that you could run is a matter of conjecture, and I'll leave it to the experimenter to find out. But you really should buy motors and use them and power them according to their recommended voltages, and you'll be fine. The other parameter is current, and current is what does the work, as we will see in some of the equations. And a motor draws the current according to this work. If there's no resistance to it, motion, the motor draws the least amount of current, and if it is stalled, the motor draws the maximum amount of current. So stall current is the amount of operating current that a motor can draw at its specified voltage. Okay. So here's another picture. Again, another set of windings, in this case one loop of winding on the rotor and the commutator and brushes, and the corresponding magnetic poles in the field. And as the equation at the top says, the torque is proportional to the current in the armature, and that comes directly from the Lorentz equation, which is shown below it, which basically says that the force generated is the cross product of the current, in this case in the armature, crossed with the B field, which is the magnetic field in the field windings, or field permanent magnet field. And it's the interaction of these two fields that generates the force, and the force at a distance produces a torque. Okay. So often DC motors are rated by their stall torque. You'll look on some data sheets, and we'll look at one in a little while, and you'll see that. And basically that is the maximum amount of torque that this particular motor can produce, and correspondingly it also implies the maximum amount of current that this particular motor can handle. It's not a good idea generally to stall motors and leave them in that condition, because they, again, will tend to overheat and in many cases will fail. Okay, we talk about the torque ratings in terms of units of load and displacement, so ounce inches or Newton meters, Newton millimeters, or millinewton meters, Newton centimeters, etc., etc. All of these are units that express this equivalent to work, if you will. Okay. So just to look at this just a little more, or a little different direction, basically if you think about it, power is torque times angular velocity. Okay, so if the torque is 0, then the power is 0. And that's in the case where the motor is spinning freely with no load on the shaft. Now note that we're ignoring the issue of internal friction in the rolling elements and shaft of the motor, etc. So yes, there is some work being done over time to make the motor turn, but that is without any load on the system. So we refer to that as a zero power condition. On the other hand, at stall, then the angular velocity is 0. And so when we have 0 velocity, we aren't producing any power. So those are the two extremes that represent the two ends of the parabolic relationship. That is the power-torque curve. And that's shown here. This is done as a normalized relationship in order to get the graphs to be of the same scale. I'll show you that on a Mathematica file here in a minute. But again, the red line represents the speed torque curve, and the blue line represents the power torque curve. And these equations just show you the relationships for speed and torque and power and torque. And note that in particular the power and torque relationship is second order, and hence the parabolic curve. Okay, so let's look at some Mathematica code. Bring that in. And so perhaps you're not familiar with Mathematica, but hopefully after this course you'll appreciate it more, and maybe you'll want to learn more about it. But it's a mathematical tool like MATLAB or MathCAD, and it's great for doing lots of mathematical analysis. In particular, I like it because it's symbolic. It does symbolic math for me, and so I like that stuff. Okay, so recall that we talked about work as being a force through a distance. It's also related to torque, torque through an angle. And torque is r cross f, or the radius times the force perpendicular to it. Okay, so here is a linear expression that relates omega, or angular velocity, to torque, and I've used b as the intercept, the y-intercept, and note that I've called that NLS, or no load speed, and that m, the slope of this linear line, is the change in speed as a function of the change in torque, or delta omega over delta tau, and it's negative, right? As the torque increases, the speed decreases. Okay, so I just picked some numbers here, say 3,000 RPM. Note that we have to change that into angular velocity of radians per second. And the speed torque, we're going to say, well, that no load speed is equivalent to 100 pi radians per second. So here's a plot of the speed torque curve from 314 radians per second down to 0 over a range of torque from 0 to 1. Now I don't have units for torque here, but quite likely it could be Newton meters or Newton millimeters or Newton centimeters, something like that. Okay, so we know that work's equal to the change in energy, and in particular if we do a lift, we lift some weight through a distance, then we've done work. And if we take the time rate of work, then we have power. Okay, so if work is also torque and angle, then power of a rotating body is torque times the angular velocity. So written an expression here for power basically as a function of angular velocity times torque. And when I put those two together, Mathematica tells me that it's tau times the quantity no load speed minus delta omega times tau over delta tau. Okay, so if I then plot that with some values, again, the no load speed is 3,000 RPM converted into radians per second, and delta omega of 100 pi radians per second, and delta tau equal to 1 unit, again probably Newton meters or Newton millimeters, and I do that for this range, then I get a plot that's shown here, this parabolic curve. Okay, so I can show those two together, and so sure enough, here's our speed torque curve, here's our power torque curve. And to finish this off, then I'm just going to normalize these curves so they look pretty, but these are what you would expect to produce from your Lab 1 results. And I don't want them normalized. I want you to plot them with real units, and you in Excel you can fix it so the two scales will match, and you'll have a nice pretty plot like I'm going to show you below. But in fact, I want you to use the actual units as measured for your system. Okay, so in Mathematica we can differentiate this power function, and the idea here is that if we differentiate the power, then we can find this maximum power point. And it turns out that it's the value there. Well, this is the expression, no load speed minus 2 delta omega tau over delta tau. And if we solve that equation for the 0 point, we find that tau is equal to this quantity, that is no load speed times delta tau over 2 delta omega. And if we use the value of no load speed at 3,000 RPM, then we can we'll come back and find that the no load speed is 100 pi. Okay, so here's that speed torque curve normalized now. Okay, and we use the peak power to calculate the power at peak, 25 pi. Okay, and so we can take the power calculation as a function of tau and divide it by 25 pi, and that's going to normalize the power curve. So again, note that the peak power now is 1, and last but not least, we can normalize these plots. So here's just the plots with the values on it, and then I've produced it with the title of the graph and the speed torque curve and the power torque curve noted with the arrows. So with that, I'll stop here and finish off with more on DC motors and how to command them here in a little bit.